somewhere beyond Mars, a machine smaller than a car is still moving, carrying a message for anyone who might find it. Voyager 1, launched in 1977, is humanity's farthest travelling object, and it has barely left our front yard. Today, we ask a question that sounds simple, but breaks physics itself. How far could humanity really travel before the universe stops us? You will see a spacecraft that could age its crew slower than the friends they left behind, a barrier faster than light that no engine can beat, and a horizon expanding faster than we can chase it. If space and mysteries like this pull you in, hit like and subscribe. It helps this channel keep exploring the edges of what is possible. Prepare yourselves. The universe has a wall, and we are about to find it. Somewhere beyond Mars, a machine smaller than a car is still moving, carrying a message for anyone who might find it. Voyager 1, launched in 1977, is humanity's farthest travelling object, and it has barely left our front yard. 12 men have walked on the moon, and every single one of them did it before 1973. Since then, no human being has travelled farther than about 250 miles from Earth, roughly the distance from Boston to Philadelphia, stretched straight up into the sky. That number sounds small compared to the promises we grew up hearing. Where are the Mars colonies? Where are the cities on the moon? The answer has nothing to do with dreaming big enough. It comes down to money, risk, and a problem that never left us. The human body was not built for the emptiness beyond our planet. Building a rocket that can escape Earth's gravity and keep a crew alive for years takes a level of funding that most governments simply stopped offering once the excitement of the space race faded. Getting to the moon cost the United States close to $250 billion in today's money. That is roughly the price of building the entire interstate highway system twice over. Once the political competition with the Soviet Union ended, so did the blank checks. Money is only half the story. The other half is written into our own bodies. Long stretches in space wear down bone density, weaken muscles, and expose astronauts to radiation levels that would make a doctor on Earth panic. On the International Space Station, astronauts orbit inside Earth's protective magnetic field, the same shield that blocks most dangerous particles from the Sun. The moment a crew leaves that shield, as the Apollo astronauts briefly did, radiation exposure jumps sharply. Stay out there for a 2-year Mars mission, and the numbers get far more serious. Here is where the real challenge shows up. Every additional day in deep space adds risk that no amount of good engineering can fully erase. Scientists still do not have a proven way to protect a human body for a multi-year journey through open space. A trip to Mars is currently the biggest target on the table, and even that would take about 7 months each way, using the fastest routes we can currently build. That is over a year just on travel without even counting the stay. The barrier is not a lack of vision. It is not a lack of rockets either. NASA and private companies like SpaceX are actively developing tools that could send humans past the moon again within this decade. The barrier is that everything past our own doorstep multiplies in danger the moment you leave low Earth orbit. And that raises the real question buried inside this whole idea of interstellar travel. If 250 miles already tests our body's limits, what happens when we start talking about millions of miles? Or trillions? The distances waiting beyond Earth are not just far. They are a different category of far, one that makes the trip to the moon look like a walk to the mailbox. To understand exactly how big that gap really is, we need to look at the fastest machine humans have ever built, and how painfully slow it actually is compared to the universe around it. In 2018, NASA launched a spacecraft that would eventually become the fastest object humans have ever built. The Parker Solar Probe was designed to do something no machine had attempted before: fly directly through the outer atmosphere of the Sun. To survive that mission, it had to move fast, and it did. At its peak, Parker reached a speed of about 430,000 miles per hour. That number is almost impossible to picture, so let's put it next to something familiar. A commercial airplane flying from New York to Los Angeles takes around 5 hours. At Parker's top speed, that same trip would take under 1 second. You could cross the entire United States faster than it takes to blink. Sounds incredible, It is incredible. But here comes the twist that changes everything about how we think of space travel. Even at 430,000 miles per hour, Parker is still painfully slow compared to the speed of light, which moves at about 670 million miles per hour. Light is roughly 1,500 times faster than our fastest human-made object. Our record-breaking probe is not even close to leaving the neighbourhood, let alone the galaxy. Now stretch that gap even further. The nearest star system to our own, Alpha Centauri, sits about 25 trillion miles away. If Parker's solar probe flew in a straight line toward it, at full speed, the trip would take almost 7,000 years. Someone who boarded that spacecraft today would not arrive until long after every language spoken on Earth right now has changed beyond recognition. This is the part most people never learn in school. Speed alone does not solve interstellar travel. Being the fastest machine humans have ever built barely makes a dent in the scale of the universe. Even multiplying Parker's speed by 10 would still leave a trip to the nearest star taking longer than all of recorded human history. Why does the gap stay so enormous no matter how impressive our engineering becomes? Rockets are limited by chemistry and physics that has not fundamentally changed since the first liquid-fueled rocket in the 1920s. Every spacecraft we launch still relies on burning fuel and pushing mass out the back to gain speed. The same basic idea as a balloon releasing air and shooting across a room. That method works well for reaching orbit or even Mars. It completely breaks down when the target is trillions of miles away, so if raw speed will not get us there, what will? Some scientists believe the answer is not a bigger engine at all, but a completely different relationship with time itself, one where the ship's clock and Earth's clock stop agreeing with each other the faster you go. That idea sounds like science fiction. It is measured, tested, and proven physics, and it changes everything about how we should imagine a real journey to another star. Right now, a trip to Mars using the fastest practical route takes about 7 months. That means an astronaut leaving Earth today would not set foot on Mars until roughly the time next year's football season begins. For a species that grew up crossing oceans in hours on a jet plane, 7 months feels like stepping backward in time. So scientists have been asking a bold question. Could new engines cut that trip down to just weeks? The current method uses chemical rockets, the same basic technology that sent astronauts to the moon. These rockets burn fuel in a huge, fast burst right at launch, then coast the rest of the way with the engines mostly off. It is like throwing a ball as hard as you can and then just watching it fly. Powerful at the start, but with nothing pushing it forward for the rest of the trip. A new idea called nuclear thermal propulsion could change that math completely. Instead of one big burn, a nuclear-powered engine heats fuel using a small reactor and keeps producing thrust for a much longer stretch of the journey. NASA and DARPA have already tested early versions of this technology, aiming for a demonstration mission before the end of this decade. Some estimates suggest nuclear propulsion could cut a Mars trip down to about 3 to 4 months, nearly cutting the current travel time in half. Even more ambitious is an idea called nuclear electric propulsion, which uses a reactor to generate electricity that powers super-efficient engines called ion thrusters. These thrusters do not produce huge amounts of force at once. Instead, they push gently but constantly for months on end, slowly building up incredible speed the way a skateboarder gains momentum by pumping their leg over and over instead of one hard shove. Here is the catch that keeps these engines on the drawing board instead of the launch pad. Building a nuclear reactor that is light enough to fly, safe enough to launch without risking an accident, and powerful enough to matter is an engineering puzzle nobody has fully solved yet. Every gram added to a spacecraft costs enormous amounts of fuel and money, and a full reactor is heavy. So could we reach Mars in weeks instead of months? With today's confirmed technology, the honest answer is no. With the nuclear engines currently in testing, a few months of travel time looks realistic within the next couple of decades. Weeks would require a leap in propulsion that has not been demonstrated yet. Something closer to the fictional engines seen in movies than anything sitting in a lab today. And that gap between Mars, our closest real destination, and the stars far beyond it, is about to get a lot more painful. Because even if we perfect every nuclear engine on the table, Mars is still practically next door compared to what comes next. The real wall in space travel is not Mars. It sits much, much farther out, at the very edge of our own sun's influence. The edge of our solar system is not where most people think it is. It is not Pluto, and it is not even close. The true boundary, called the heliopause, is the point where the sun's stream of particles, called the solar wind, finally gets overpowered by the empty space between stars. That boundary sits about 11 billion miles from the sun, roughly 120 times farther away than Earth. Only one human-made object has ever crossed that line. Voyager 1, launched in 1977, finally reached interstellar space in 2012 after travelling for 35 years. 35 years just to leave the solar system, using one of the fastest launches ever attempted, boosted by a rare planetary alignment that only comes around once every few decades. Now picture a human crew trying to make that same trip. Even if astronauts could survive the radiation, the isolation, and the psychological toll of decades locked inside a metal capsule, the math alone rules it out for a normal human life. Someone leaving Earth at 30 years old would be turning 65 by the time they crossed into interstellar space, using Voyager's speed as the benchmark, and crossing that boundary is only the beginning. It is simply the moment you leave your own backyard. This is where a comparison helps. Imagine the solar system as a house, with Earth sitting on the front porch. The sun's outer edge, the heliopause, would be the edge of the entire property line, maybe half a mile down the road. Getting there and back using today's fastest technology would eat up almost your entire adult life. And the nearest star beyond our own is not the neighbour's house. It is a different city, hundreds of times farther than that walk down the road. Some engineers have proposed faster missions specifically designed to reach interstellar space quicker than Voyager did. A concept called Interstellar Probe, studied by Johns Hopkins University, could use a close pass by the Sun combined with a gravity assist to reach interstellar space in about 15 years instead of 35. That is a real improvement. It is also still longer than most people spend in a single career. Even with every clever trick gravity assists nuclear engines, ultralight spacecraft, leaving the solar system remains one of the slowest milestones in space exploration, relative to how close it actually is on a cosmic map. It takes decades to cross a distance that, compared to the size of our galaxy, barely counts as a step out the front door. So if simply exiting our own solar system eats up half a human lifetime using our best technology, the real question becomes almost frightening to ask. What happens when the target is not 11 billion miles away, but 25 trillion? To understand that scale, we need to follow the one machine that has actually made this journey and see exactly what leaving home really cost it. Voyager 1 carries a message meant for someone who is not us. Bolted to its side is a golden record, packed with music, greetings in 55 languages, and images meant to explain human life to any intelligent being that might one day find it drifting through the dark. Launched on September the 5th, 1977, it was never designed to travel forever. Yet here we are, nearly 50 years later, and it is still sending signals home. Voyager 1's original mission was simple by comparison to what it became. Fly past Jupiter and Saturn, take pictures, gather data, then quietly finish its job. Instead, engineers realized the spacecraft still had enough power and fuel to keep going, so they extended the mission again and again. It flew past Jupiter in 1979, then Saturn in 1980. After that, it kept pushing outward, past every planet, past every asteroid belt, into territory no machine had ever mapped before. In August of 2012, something historic happened. Voyager 1 crossed the heliopause and became the first human-made object to enter interstellar space, the vast region between stars. Scientists confirmed it by measuring a sudden jump in the density of particles around the spacecraft, a clear signature that it had left the sun's protective bubble behind. It had taken 35 years to get there. Today, Voyager 1 sits more than 15 billion miles from Earth, so far away that a radio signal, travelling at the speed of light, takes over 23 hours just to reach it. Send a message, and you wait almost a full day for any kind of reply. Compare that to a phone call to the other side of Earth, which takes a fraction of a second. Voyager exists in a kind of communication delay that makes real conversation impossible. The spacecraft still runs on a shrinking supply of plutonium-powered energy, and engineers have had to shut down instruments one by one to keep the essential systems alive. Scientists expect Voyager 1 will finally go silent sometime around 2025, unable to power even its most basic transmitter. After that, it will keep drifting in complete silence, carrying its golden record through the galaxy for possibly billions of years, long after the Sun itself has changed and Earth has gone through changes no human alive today will witness. Here is the number that puts everything into perspective. Voyager 1 is humanity's farthest travelling object, moving faster than almost anything we have ever built. And yet, at its current speed, it would still take about 75,000 years just to reach the nearest star system, Alpha Centauri, and that is not even its actual destination. Our fastest, farthest, most successful mission in history is still nowhere near reaching another star. If our best machine cannot even get close, the next question becomes unavoidable. Why can't engineers simply design something faster? Build a bigger engine, add more fuel, solve the problem with raw power? The answer to that question is where space travel stops being an engineering problem and starts becoming a battle with the laws of physics themselves. Every rocket ever built follows the same basic rule. It carries fuel, burns that fuel, and shoots the exhaust out the back to push itself forward. This idea is called reaction propulsion, and it works the same way a balloon zooms across a room when you let go of it without tying the end. The gas rushes out one side and the balloon shoots the other direction. Simple, reliable, and used since the very first rockets left Earth. Here is the problem hiding inside that simple idea. The faster you want to go, the more fuel you need. But that extra fuel adds weight, and that extra weight needs even more fuel to push it. Engineers call this the rocket equation, and it grows out of control fast. Doubling a rocket's final speed does not just double the fuel needed. It can multiply it several times over, because the rocket has to carry the weight of its own fuel the whole way. Picture trying to fill a car's gas tank for a trip so long that the extra gas weighs down the car so much it needs even more gas just to carry that gas. At some point, you're hauling more fuel than the car can physically handle, and the math simply stops working. That is exactly what happens when engineers try to push chemical rockets towards speeds anywhere close to the speed of light. The fuel required becomes heavier than the entire visible universe, long before the ship gets anywhere close to interstellar speeds. Simply building a bigger, more powerful version of the same engine will never solve interstellar travel. It is not a matter of trying harder or spending more money. It is a wall built directly into the mathematics of how rockets work. Every chemical and nuclear engine humans have ever designed runs into the same trap the closer it gets to extreme speeds. So scientists have had to think in a completely different direction. Instead of asking how to carry more fuel, they started asking whether a spacecraft needs to carry fuel at all. Ideas like solar sails use sunlight itself as a source of gentle, constant push, the same way wind fills a sailboat without the boat needing to carry its own air supply. Other concepts use lasers fired from Earth to blast a spacecraft's sail from behind, accelerating it without adding a single extra pound of onboard fuel. These ideas sound strange, almost impossible, yet a real mission called Breakthrough Starshot is actively developing this exact concept, aiming to push a tiny probe to 20% of the speed of light using a laser array on Earth. At that speed, a trip to Alpha Centauri would take about 20 years instead of thousands. But even solving the fuel problem does not remove every obstacle standing between humans and the stars. Once a spacecraft gets close enough to serious fractions of light speed, something even stranger starts happening. Time itself stops behaving the way we expect. The ship's clock and Earth's clock begin drifting apart, and that strange twist in reality may be the biggest key to interstellar travel we have. Albert Einstein discovered something in 1905 that still sounds impossible today. Time does not move at the same rate for everyone. It bends, stretches, and slows down depending on how fast someone is moving. Scientists call this time dilation, and it has been measured, proven, and confirmed thousands of times using real experiments. Here is the simplest way to picture it. Imagine two friends with perfectly synced watches. One stays on Earth. The other boards a spacecraft and flies at close to the speed of light for what feels, to them, like exactly 1 year. When that traveller returns home, their watch shows 1 year has passed, but the friend who stayed on Earth might find that 10 years have gone by, or 50, or even more, depending on exactly how fast the ship was moving. Both watches are correct. Time itself moved differently for each person. This might sound like something out of a movie, but airplanes, satellites and GPS systems prove it every single day. Satellites orbiting Earth move fast enough and sit in a different level of gravity that their onboard clocks tick at a slightly different rate than clocks on the ground. If engineers did not correct for this tiny time difference, every GPS map on every phone would drift off by miles within a single day. The effect is small at everyday speeds, but it's completely real. Now stretch that same effect toward the extreme. The closer an object gets to the speed of a light, the more dramatic the time difference becomes. At 90% of light speed, time on a spacecraft would move at less than half the rate it does on Earth. At 99.9% of light speed, a single year on board could equal decades back home. Push even closer to 100% and the numbers become almost unbelievable, with 1 year on board potentially matching centuries on Earth. This creates one of the strangest possibilities in all of space travel. A spacecraft could, in theory, cross distances that should take thousands of years, and the crew on board would only experience a fraction of that time. Nothing can travel faster than light. Their own personal clock simply moves slower the entire way. The catch, and it is a massive one, is that reaching those extreme speeds requires an amount of energy so enormous that no engine humans have ever built comes anywhere close. Getting a spacecraft to even 10% of light speed remains far beyond current technology, let alone 99%. Still, this single idea, that speed itself can bend time, opens a door that engine power alone never could. It suggests that a journey which looks impossible from Earth's perspective might feel completely different to the people actually making the trip. If a crew's own clock could run slow enough, could they reach another star system within a single human lifetime, even if Earth watched decades or centuries pass by during that same trip? Alpha Centauri sits about 25 trillion miles from Earth. At the fastest speed any human-made object has ever reached, that trip would take tens of thousands of years. But time dilation changes this entire calculation once a spacecraft approaches a serious fraction of light speed, and the results are strange enough to sound like fiction. Picture a spacecraft that could somehow reach 99% of the speed of light, a speed no current engine can produce, but one that stays within the laws of physics. From Earth's perspective, the trip to Alpha Centauri would still take a little over 4 years, since light itself takes about 4.2 years to cover that distance. But the crew on board would experience something completely different. Because of time dilation, their own clocks would slow down so much that the journey might feel like it took only about 7 months. Push the speed even further, to 99.9% of light speed, and the crew's experienced time drops even more, potentially down to just a few weeks for the same trip that still takes over 4 years back on Earth. The ship is not moving faster than light. It is bending its own relationship with time so severely that distance itself seems to shrink from the traveller's point of view. This means a single human lifetime could, in theory, be enough to reach not just the nearest star but potentially dozens of star systems, one after another, as long as the ship kept accelerating to extreme speeds between each stop. A 20-year-old astronaut could, in theory, visit several nearby stars and return home still relatively young, biologically speaking. Here comes the twist that turns this incredible possibility into a heavy trade-off. While the crew ages slowly, Earth does not slow down at all. Every year that passes for the astronauts could mean many more years passing back home. A crew that left Earth for what feels like a 7-month trip to Alpha Centauri and back would return to find that everyone they knew has aged over 8 years, if not more, depending on the exact speeds involved. Push the mission farther, to more distant stars, and that gap could stretch into decades or even centuries. This is a direct mathematical consequence of how the universe actually works, confirmed by real physics experiments, not guesswork. Travelling near light speed does not just move a person through space, it moves them through time unevenly compared to everyone they left behind. So reaching another star in a single lifetime might be one of the more realistic paths to interstellar travel we have, assuming humans can ever build an engine capable of reaching those speeds. But it comes with a cost that few people consider when they picture the future of space travel. What would it actually feel like for a crew to leave Earth for what feels like months, only to return to a world that has moved on without them for years? Imagine two twin siblings, both 30 years old. One boards a spacecraft heading toward a distant star at close to the speed of light. The other stays home, living a completely normal life on Earth. When the travelling twin returns, they step off the ship still looking 30, maybe 31. Their sibling, the one who never left, is now approaching old age, decades older than the twin who never physically aged past their journey. This scenario, known among physicists as the twin paradox, is one of the most well-tested predictions in all of physics. The travelling twin genuinely experiences less time passing, in every physical, biological and measurable sense. Their heart beats fewer times, their cells divide fewer times. Every clock on board their spacecraft, from a wristwatch to the ship's main computer, ticks at a slower rate compared to every clock left behind on Earth. The reason comes back to time dilation, but here is the deeper piece most people miss. Time itself genuinely moves at a different rate depending on how fast someone travels through space. Moving through space at extreme speed literally means moving through time more slowly, as if speed borrows a bit of your future clock and uses it for your journey instead. This creates a strange kind of one-way ticket. A crew that spends what feels like 5 years exploring a distant star system might return home to find that 50 years have passed on Earth. Children they left behind could now have children of their own. Technology could look completely different. Entire political systems, entire cultures could shift in ways the crew never witnessed happening in real time. Some scientists have pointed out that this effect, while strange, could actually make certain kinds of missions easier for the people on board. A crew heading toward a star hundreds of light years away might personally experience only a decade or two of travel time, even though Earth watches centuries pass by. In a sense, extreme speed acts like a built-in form of time travel into the future, one that only moves in a single direction and can never be reversed. But this creates a heavy psychological weight for any future astronaut considering such a mission. Leaving Earth would mean leaving behind an entire era, an entire generation of people, knowing they will likely be gone or drastically change by the time the ship returns, if it returns at all. This single effect, more than almost anything else in the science of interstellar travel, forces us to rethink what returning home would even mean, and it raises a bigger question about the speed itself. If getting close to light speed bends time this dramatically, what exactly stops us from just continuing to push faster until a spacecraft finally reaches light speed itself, or even beyond it? Light travels at about 670 million miles per hour, a number so large it barely feels real. In one single second, light could circle the entire Earth about 7.5 times. For over a century, physicists have understood one unbreakable rule connected to that number: nothing with mass can ever reach or exceed it. This is not a limit caused by weak engines or unfinished technology. It is written directly into the structure of the universe itself, a conclusion Albert Einstein reached through his theory of special relativity. As an object with mass moves faster, it requires more and more energy to keep accelerating. Near the speed of light, the amount of energy needed grows without any limit at all. Here is a comparison that makes this click. Imagine trying to fill an empty swimming pool using a garden hose, but every bucket of water you add makes the pool slightly bigger, requiring even more water to fill it completely. No matter how long you keep pouring, the pool keeps growing faster than you can fill it. Pushing a spacecraft toward light speed works the same way. Every bit of extra speed demands a disproportionately larger amount of energy, until reaching light speed itself would require an infinite amount, more energy than exists in the entire universe. Light speed acts less like a speed limit and more like a mathematical wall. Photons, the particles that make up light, have no mass at all, which is exactly why they can travel at that speed without needing infinite energy. Anything with mass, including a spacecraft, a human body, or even a single grain of dust, simply cannot follow the same rule. Some people ask whether future technology could somehow break this barrier, the same way engineers once broke the sound barrier with faster aircraft. The sound barrier was a barrier of air pressure, a physical obstacle that clever engineering could push past. The light speed barrier is built into the geometry of space and time itself, confirmed repeatedly through decades of experiments involving particle accelerators, which have pushed particles to over 99.9% of light speed without a single one ever crossing that final line. So if reaching light speed is truly impossible, does that mean interstellar travel is hopeless? Many physicists say no. Getting close to light speed, even at 99%, still unlocks the powerful time dilation effects we already explored, effects that could make distant stars reachable within a human lifetime, even if the ship itself never crosses the final line. But scientists have not given up looking for loopholes elsewhere. If a spacecraft can never outrun light directly, could there be another path through the universe entirely, one that avoids the speed limit altogether by bending space itself instead of racing across it? This question leads directly into one of the strangest and most debated ideas in all of physics: the possibility of a wormhole. Picture a single sheet of paper with two dots drawn on opposite ends. To travel between those dots, you would normally need to walk the entire length of the paper. But what if you could fold the paper in half, bringing the two dots close enough to touch, then simply poke a hole straight through both of them? That is the basic idea behind a wormhole, a theoretical shortcut through the fabric of space itself. This idea comes directly from Einstein's own equations describing gravity, first explored in a serious way by Einstein and physicist Nathan Rosen in 1935. Their math showed that space and time, together called spacetime, could theoretically bend and connect two distant points, creating a tunnel that skips the distance in between entirely. Scientists still call this an Einstein-Rosen bridge in his honour. If a real, stable wormhole existed, the implications would be staggering. A journey that would normally take tens of thousands of years crossing regular space could, in theory, take moments through a wormhole connecting the same 2 points. Distance itself would stop being the obstacle, because the ship would never actually cross the space in between. It would step through a shortcut instead. Here is where the excitement runs into serious trouble. Every piece of math describing a wormhole suggests it would be violently unstable. The moment anything, even a single particle of light, tried to pass through, the wormhole's own gravity would likely cause it to collapse and pinch shut instantly. Faster than anything could make it to the other side. Some physicists compare it to trying to walk across a bridge that collapses the instant your foot touches it, over and over, no matter how many times you try. Scientists have proposed a possible fix, something called exotic matter, a theoretical form of matter with negative energy that could, in theory, hold a wormhole open long enough for something to pass through safely. Exotic matter has never been observed or created anywhere in the universe. It exists purely as a mathematical possibility, something allowed by the equations but never confirmed to actually exist. There is also the question of where a wormhole would even come from in the first place. Nothing in our current understanding of physics gives scientists a realistic way to create one artificially. Even if a natural wormhole exists somewhere in the universe, finding it, confirming it is stable, and then safely piloting a spacecraft through it remains completely outside anything humans currently know how to do. A wormhole remains one of the most exciting shortcuts allowed by the math of physics, and also one of the least likely to ever become real. It sits in a strange category of ideas that are theoretically possible, but practically almost unreachable. If a shortcut through space seems nearly impossible, what about a completely different trick? One that does not tunnel through space, but instead warps space itself around a ship, pulling the destination closer without ever technically moving faster than light. Even in the rare scenario where a wormhole could somehow form and stay open long enough to matter, surviving the trip through it presents an entirely separate mountain of problems. Physicists studying these theoretical tunnels have found that the environment inside would likely be far more hostile than the vacuum of regular space. The first problem comes from gravity itself. Most theoretical models of wormholes predict enormous tidal forces near the entrance and exit points, similar to the crushing forces found near a black hole. Tidal forces happen when gravity pulls harder on one part of an object than another. Near an extreme gravitational point, the pull on your feet could be dramatically stronger than the pull on your head, stretching a human body like taffy being pulled apart at both ends. Scientists have a blunt nickname for this process: spaghettification. Radiation adds another layer of danger. Many theoretical wormhole models suggest that any matter or energy passing through the tunnel would get compressed and intensified, similar to squeezing toothpaste through an increasingly narrow tube. Light and particles entering one side could exit the other side, amplified into a blast of radiation strong enough to destroy any spacecraft and any crew almost instantly. Then there is the exotic matter problem again. The same theoretical negative energy material that might be needed to hold a wormhole open in the first place. Even if scientists somehow created or found this material, nobody knows what side effects it would have on anything passing near it. Negative energy has never been observed in a large enough amount to study safely, so its interaction with the human body remains a total unknown, one that could range from harmless to instantly fatal. Some physicists have proposed narrower, more stable wormhole designs that could theoretically reduce these dangers, but every version still relies on physics that has never been tested, built, or confirmed outside of pure mathematics. It is the difference between a bridge that exists only as a blueprint and a bridge that has actually been built and driven across safely 1,000 times. This combination of extreme gravity, dangerous radiation, and completely unknown exotic matter effects is why most physicists treat wormhole travel as a fascinating mathematical possibility, rather than a realistic plan for the future. It might be allowed by the equations. It might still be a death sentence for anyone brave enough to attempt it. Even the universe's own shortcuts come loaded with fatal catches. Scientists have looked toward a different, less violent idea, one that does not require punching a hole through space-time at all. Instead of tunneling through the fabric of the universe, what if a spacecraft could simply grab a piece of space itself, compress it in front of the ship and stretch it out behind, riding a wave through the cosmos without ever technically breaking the light speed barrier? This idea has a name, and it comes with its own almost unbelievable price tag. In 1994, a physicist named Miguel Alcubierre proposed an idea that sounded like it belonged purely in science fiction, except it came from real, working equations inside Einstein's theory of general relativity. Instead of moving a spacecraft through space the normal way, Alcubierre's concept involved moving space itself around the spacecraft. Picture space as a giant sheet of rubber. Normally an object sits still on that sheet unless something pushes it. But what if, instead of pushing the object, you could stretch the rubber sheet behind it and compress the rubber sheet in front of it? The object would appear to move forward rapidly, even though it never actually moved relative to the space immediately surrounding it. This is the basic idea behind what scientists now call a warp bubble. Inside this bubble, the spacecraft and its crew would remain completely still, relative to the space right around them. Meanwhile, space itself would contract in front of the ship and expand behind it, effectively carrying the bubble across vast distances. Because the ship is not technically moving through space faster than light, only the space around it is changing shape. This concept does not violate Einstein's light speed limit at all. It finds a loophole instead of breaking the rule directly. If this could actually be built, the results would be staggering. A warp bubble could theoretically carry a spacecraft to Alpha Centauri in a matter of days or weeks, rather than years or centuries, all without the crew experiencing any of the extreme time dilation effects that come with approaching light speed through normal acceleration. From the crew's perspective, and from Earth's perspective, the trip would simply happen fast. Here is where the excitement collides head-on with reality. Alcubierre's original equations required an amount of energy so enormous that early estimates suggested it would take converting the entire mass of a planet the size of Jupiter directly into pure energy just to power a single small ship. Later refinements to the math brought that number down significantly, but even the most optimistic modern estimates still call for energy levels far beyond anything humanity currently knows how to generate or store. There is also the same exotic matter problem that haunts wormhole travel. Creating and controlling a warp bubble appears to require negative energy density, a theoretical form of energy that has never been observed in large, usable amounts anywhere in the universe. Some laboratory experiments have detected tiny, fleeting hints of negative energy on a microscopic scale, but nothing close to what a warp bubble would demand. Scientists at NASA and several universities continue studying warp drive concepts seriously, refining the math and searching for ways to reduce the staggering energy requirements. It remains one of the only faster-than-light concepts still taken seriously within mainstream physics. Precisely because it does not break Einstein's rules, it simply bends them in an extremely creative way. The blueprint for a warp bubble technically exists on paper. Building the power source to actually run it is where this dream currently collapses. That collapse comes down to one brutal number: one so large it makes even Voyager's decades-long journey look laughably cheap by comparison. Let's put a real number on the warp drive problem, because the size of it is almost impossible to imagine without one. Early calculations for Alcubierre's original warp bubble design suggested the ship would need roughly the same amount of energy contained in the mass of an object, 100 times larger than the planet Jupiter. Converting an object like that entirely into usable energy is a scale of energy larger than what most stars produce over their entire lifetimes. To make that number feel real, picture the largest nuclear power plant on Earth, one capable of powering an entire major city. Now imagine that plant running continuously for the entire age of the universe, nearly 14 billion years, without a single day of downtime. Even that staggering amount of energy would still fall short of what early warp drive models required for a single trip. Later researchers managed to shrink this number considerably by reshaping the geometry of the theoretical warp bubble. A physicist named Harold White, working with NASA, proposed adjustments that could reduce the energy requirement from planet size to something closer to the mass of a small spacecraft itself. That sounds far more reasonable, until you remember it still means converting solid matter directly into pure energy on a scale humanity has never even come close to achieving in a controlled, safe way. Here is the deeper issue hiding behind these massive numbers. Even our best current source of energy, nuclear fusion, the same reaction that powers the sun, converts only a small fraction of matter into usable energy. Humanity has not even mastered controlled fusion power on Earth yet, despite decades of research and billions of dollars invested. Jumping from unmastered fusion straight to full matter, to energy conversion, the kind used in these warp calculations, represents a leap similar to asking someone who's never ridden a bicycle to immediately pilot a jet. There is also the unresolved need for exotic matter, the same negative energy material required for wormholes. Without it, the warp bubble concept simply does not function according to the math, no matter how much energy gets thrown at the problem. Scientists have never observed usable amounts of this material anywhere in nature. Some researchers remain hopeful. They point out that flight itself once seemed impossible, and nuclear power seemed like fantasy before physicists understood how atoms actually worked. Reducing warp energy requirements from planet-sized down to spacecraft-sized in just a few decades of study represents real progress, even if the finish line remains far out of reach. For now, warp travel exists purely as an elegant idea on paper, one blocked by a wall of energy so large that current human civilization uses only a tiny fraction of it collectively, across every power plant on the planet, every single year. Getting anywhere close to interstellar warp travel would likely require harnessing energy sources far beyond anything humans currently understand how to build. Both wormholes and warp bubbles remain stuck behind the same wall, exotic matter and impossible energy requirements. If space itself refuses to bend for us, scientists have also explored a more direct approach, one that skips shortcuts entirely and instead asks whether a spacecraft could get close to light speed the hard way, using the most powerful fuel source known to physics. Every particle in the universe has an opposite twin made of antimatter. An electron has a positive counterpart called a positron. A proton has a negative counterpart called an antiproton. These particles have been created and studied in laboratories since the 1930s. What makes antimatter special and dangerous is what happens the instant it touches regular matter. When matter and antimatter meet, they completely destroy each other, converting 100% of their combined mass directly into pure energy. Compare that to a nuclear power plant, which converts less than 1% of its fuel's mass into usable energy through fission. Even nuclear fusion, the reaction that powers the sun, converts less than 1% of its fuel into energy. Antimatter annihilation converts everything. Gram for gram, it is the most powerful energy source physics allows. This makes antimatter engines one of the most seriously studied propulsion ideas for reaching extreme speeds. A spacecraft powered by matter, antimatter annihilation, could theoretically reach a significant fraction of light speed using a fuel supply thousands of times smaller and lighter than any chemical rocket would need for the same speed. Some early NASA studies have looked at antimatter propulsion specifically for future missions to distant parts of the solar system and beyond. Here is the massive obstacle standing in the way. Antimatter does not simply exist somewhere waiting to be mined or collected. It has to be manufactured, one particle at a time, inside massive machines called particle accelerators. The entire global supply of antimatter ever created by humans, across every laboratory on Earth, over decades of research, adds up to a fraction of a single gram. Producing even that tiny amount has cost billions of dollars combined. To put the challenge in perspective, scientists estimate that producing just 1 gram of antimatter, using our current best technology, would take an enormous amount of energy and cost more than the entire global economy produces in several years. A single gram sounds small, about the weight of a paperclip, yet it is currently far beyond anything humanity can practically produce or afford. There is also the problem of storage. Antimatter destroys itself instantly upon touching regular matter, which means it cannot be held in a normal container. Scientists currently store tiny amounts using powerful magnetic fields that keep the antimatter suspended, never touching any physical surface. Scaling that storage method up to something large enough to fuel an actual spacecraft engine remains a serious unsolved engineering challenge. Antimatter offers something no other fuel source can match, an almost perfect rate of converting mass into energy. It also comes with a price tag and a production challenge that makes it, for now, one of the most theoretically powerful and practically unreachable propulsion ideas on the table. If humanity ever solves antimatter production and storage, the payoff could be enormous. Until then, this dream fuel remains locked behind a problem that goes beyond physics and lands squarely in economics. To understand exactly why, we need to look at just how expensive and how rare a single gram of antimatter truly is. If someone wanted to buy a gram of gold today, it would cost around $65. A gram of a rare diamond could run into the thousands. But a gram of antimatter carries a price tag that makes every other expensive material on Earth look like pocket change. NASA physicist Gerald Smith once estimated that producing just 1 gram of antimatter, using the technology available at the time, would cost around $62.5 trillion. To understand why the cost is so extreme, picture how antimatter actually gets made. Facilities like CERN in Switzerland use massive particle accelerators, tunnels stretching for miles underground, to smash regular particles together at incredible speeds. Occasionally, out of billions of collisions, a tiny handful of antimatter particles get created as a byproduct. Scientists then have to carefully capture and store each of these particles using powerful magnetic fields, since even the smallest contact with regular matter would destroy them instantly. The scale of inefficiency here is staggering. Producing antimatter currently takes far more energy than the antimatter itself would ever release if used as fuel. It would be like spending $1,000 in electricity just to charge a battery worth $1. Every antimatter particle created at a facility like CERN represents a tiny expensive fragment, and combining enough of these fragments into even a single visible speck would take the facility's entire operating capacity running for years. This cost problem connects directly back to why antimatter engines remain purely theoretical. Even if scientists solved every engineering challenge involved in storing and safely using antimatter as fuel, the raw production cost alone currently sits far beyond the entire economic output of every country on Earth combined multiple times over. A single gram, roughly the size of a raindrop, would cost more than human civilization currently produces in economic value across several decades. Some researchers remain optimistic that production costs could fall dramatically with future breakthroughs, the same way computer chips became millions of times cheaper over the past several decades. Faster, more efficient particle accelerators could theoretically increase antimatter production rates and drive costs down significantly. But even the most hopeful projections still describe a technology many decades, possibly centuries, away from producing antimatter cheaply enough to fuel an actual spacecraft. For now, antimatter remains locked in a strange position. It offers the most powerful energy conversion physics allows, while simultaneously being the most expensive material humans have ever attempted to create. It sits on the very edge of what modern civilization can achieve, a fuel source that exists in laboratories only in amounts too small to see with the naked eye. Even if humanity eventually solves the impossible cost of antimatter, another danger waits quietly in the space between stars, one that has nothing to do with fuel, engines, or energy at all. It involves the empty darkness itself, which turns out to be far less empty and far more dangerous than it first appears. Space looks completely empty in every photograph ever taken, black, silent, and seemingly free of anything solid for trillions of miles in every direction. This image is misleading. The regions between stars actually contain a thin, scattered mixture of gas and dust called the interstellar medium, and while it is far less dense than anything on Earth, it is not nothing. To understand just how thin this material really is, picture the emptiest vacuum ever created inside a laboratory on Earth. Even that artificial vacuum contains more particles per cubic inch than the average patch of interstellar space. On average, interstellar space contains roughly 1 atom per cubic centimetre, compared to the air around you right now, which contains about 25 quintillion molecules in that same tiny space. By any normal measurement, interstellar space really is close to a perfect vacuum. Here is where the danger comes in, and it has nothing to do with the emptiness itself. It comes from speed. A spacecraft sitting still would never notice these scattered particles. But a spacecraft moving at a significant fraction of the speed of light turns even a single stray atom into something far more dangerous. Think about how getting hit by a single raindrop while standing still feels like nothing at all. Now imagine getting hit by that same raindrop while riding a motorcycle at highway speed. The raindrop has not changed. Your speed relative to it has, and that changes everything about the impact. A spacecraft moving at even a modest fraction of light speed would experience every stray atom and dust grain in its path with an equivalent force multiplied by an almost unimaginable amount. Scientists studying interstellar travel concepts, including the team behind Breakthrough Starshot, have taken this threat seriously in their planning. At speeds approaching 20% of light speed, even a microscopic dust grain could strike a spacecraft with the destructive force of a small explosion, capable of punching through hull material that would easily stop a bullet under normal conditions. At speeds even closer to light itself, individual hydrogen atoms scattered through space could deliver damaging radiation exposure to anything without serious shielding. This creates a genuine engineering puzzle for any theoretical high-speed mission. Protecting a spacecraft from these microscopic threats would likely require some combination of thick forward shielding, clever magnetic fields designed to deflect charged particles away from the hull, or carefully mapped travel routes designed to avoid the densest patches of interstellar material. Every solution adds weight, complexity, and cost to a mission that already pushes the limits of known physics. The seemingly empty gap between stars turns out to be one more serious obstacle, standing between humanity and interstellar travel, hiding in plain sight inside the very darkness that looks so calm and silent from a distance. It is a threat built entirely out of speed itself, a danger that barely exists at rest and grows catastrophic the faster a ship moves. This raises an important question about the destination itself. Even if a crew somehow survives the empty dangers of interstellar space, dodges every stray particle, and reaches a nearby star system alive, how far away is that star really? And once we understand that true distance, does it even count as close compared to everything else still waiting, undiscovered in the galaxy beyond it? Alpha Centauri is not one star. It is 3, locked together in a slow cosmic dance about 4 light-years from Earth. 2 of them, Alpha Centauri A and Alpha Centauri B, are bright and sun-like, circling each other the way 2 dancers spin around a shared centre. The third, a small dim star called Proxima Centauri, sits slightly closer to us than its 2 bigger neighbours, making it the actual nearest star to our own Sun. Proxima Centauri lies about 4.2 light-years away. A light-year measures distance, not time, the distance light travels in 1 full year. So when astronomers say 4.2 light-years, they mean a beam of light leaving that star today would take over 4 years just to reach your eyes. Compare that to the Moon, where light takes about 1 second to arrive, and the distance gap becomes almost impossible to picture using anything from daily life. Here is what makes Proxima Centauri exciting instead of just distant. In 2016, astronomers discovered a planet orbiting it, now called Proxima b. This rocky world sits inside the star's habitable zone, the narrow region where temperatures could allow liquid water to exist on a planet's surface. Scientists have not confirmed alien life there, and they may never get the chance to check up close. Even naming it a genuine science-based target for a future mission changes the entire conversation about interstellar travel. Sending a probe to Alpha Centauri A and B the brighter binary pair, would mean crossing roughly 4.4 light-years, a small step farther than reaching Proxima alone. Every serious plan for humanity's first interstellar mission points toward this same tiny patch of sky, simply because nothing else comes remotely close in distance. The next nearest star system after that sits nearly twice as far away. 4.2 light-years might sound almost reachable after everything explored so far. It is not a walk down the street, but compared to crossing an entire galaxy, it looks almost like a neighbour's house. This is the frustrating tease sitting at the centre of interstellar travel. The closest possible target still requires crossing a distance that light itself needs over 4 years to cross, and human spacecraft move nowhere near that fast. Scientists studying interstellar missions treat Alpha Centauri as the finish line for humanity's first real attempt to leave home for another star. Every propulsion idea explored so far gets measured against this exact same distance, because it represents the shortest possible test of everything discussed. If humanity cannot make this trip work in any reasonable amount of time, then farther stars stay completely off the table. So the target exists, the distance is fixed, unavoidable, and already known with precision down to the mile. The only question left is whether human technology, even with every breakthrough currently being researched, could actually cover that gap fast enough for real people to survive the journey and still find a familiar world waiting when they return, or whether reaching even our closest stellar neighbour demands sacrificing generations instead of years. Cutting-edge nuclear fusion engines, the kind still sitting on drawing boards inside research labs today, could theoretically push a spacecraft to around 10% of the speed of light. That number sounds thrilling after everything explored about chemical rockets and their painfully slow crawl through space. At that speed, reaching Proxima Centauri would take a little over 40 years, a single working lifetime rather than tens of thousands of years. Here is the catch buried inside that exciting number. 10% of light speed remains a theoretical target, built entirely around fusion technology that has never actually flown on a real spacecraft. Every fusion propulsion design studied so far exists only on paper or inside small laboratory experiments, decades away from powering an actual mission. Realistic propulsion available within the next several decades looks far more modest, closer to 1% of light speed at best, using advanced ion engines or nuclear electric systems. At 1% of light speed, the trip to Proxima Centauri stretches out to roughly 400 years. Nobody who boards that spacecraft would live to see it arrive. Their grandchildren would not see it either. The great-grandchildren of the original crew, people who never knew Earth firsthand, would be the ones who finally watched a new star grow larger through the ship's windows. Think about how strange that idea really is. Imagine boarding a ship today, knowing you will spend your entire life inside it. Your children will spend their entire lives inside it, and only your distant descendants, born and raised in space, will ever step onto solid ground again. Every person who ever knew Earth personally will have died decades or centuries before arrival. This shifts the entire nature of interstellar travel. It stops being a mission for astronauts and starts becoming something closer to founding a permanent self-contained civilization that happens to be moving through space instead of staying still. The ship itself becomes the only home multiple generations will ever know, built entirely for a destination none of the original crew will personally reach. Scientists studying long-duration missions call this concept a generation ship, and it forces a completely different set of questions than a quick scientific mission ever would. Feeding a crew for 40 years is difficult. Feeding, educating, and sustaining a healthy, functioning society for 400 years, sealed inside a metal shell with no chance of resupply, becomes a challenge unlike anything humanity has ever attempted. Even faster propulsion concepts still under research, ones that might someday reach speeds high enough to make the trip in a single lifetime, remain firmly in the experimental stage, tested only in small-scale demonstrations rather than full missions. Until something dramatically better than today's best engines becomes real and reliable, any serious plan for reaching even our closest neighbouring star system means accepting a truth most people rarely consider. The first humans to leave Earth for another star may never see their destination themselves, and neither will their children. That single fact changes everything about what a real interstellar mission would actually require, not just in engineering, but in biology, psychology, and the very structure of a small human society sealed away from the rest of our species for centuries at a time. A generation ship is exactly what it sounds like. a spacecraft built to carry not just a crew, but an entire self-sustaining society, one that lives, ages, and reproduces across multiple human generations during a single uninterrupted journey. Nobody has ever built one. Every version that exists today lives only inside scientific papers, engineering studies, and detailed simulations run by researchers trying to figure out if the idea could actually work. The first challenge is simply keeping people alive. A generation ship needs a completely closed life support system, one that recycles air, water, and waste with almost perfect efficiency for centuries without a single resupply mission from Earth. The International Space Station, humanity's most advanced closed environment so far, still depends on regular supply shipments from the ground. Removing that safety net entirely for 400 years straight means every single failure has to be fixable using only the materials already on board. Growing food presents its own massive puzzle. A generation ship would likely need farms built directly into the hull, using carefully controlled lighting, water, and soil systems to grow enough crops to feed potentially thousands of people across many decades. Scientists studying this problem estimate a genuinely self-sustaining population would need somewhere between several hundred and several thousand people, a number large enough to maintain healthy genetic diversity across generations, since a smaller starting population risks serious health problems from limited genetic variety over time. Then comes a problem that has nothing to do with biology or engineering at all. Sociologists studying generation ship concepts have raised serious concerns about culture and purpose. The first generation would leave Earth voluntarily, fully understanding and accepting the mission. Their children, and every generation after that, would be born already trapped inside a metal shell, never given a choice about the life-altering decision that shaped their entire existence. Some researchers worry this could create deep resentment, social breakdown, or even organised rebellion against a mission those later generations never personally agreed to join. There is also the psychological weight of total isolation. Every person aboard would live their entire life inside a structure smaller than a small town, surrounded by the same limited group of people for their whole existence, with zero possibility of leaving, visiting anywhere else, or even seeing another human being outside the ship. Researchers who study isolation in places like Antarctic research stations already see serious mental health struggles develop after just a few months of confinement. Stretching that same isolation across an entire human lifetime, and then across many lifetimes in a row, represents psychological territory nobody has ever actually tested. Every problem here connects to every other problem. A society breakdown threatens food production. Failing food production threatens survival. Survival threats create panic, which threatens social stability even further. A generation ship is not simply a really long camping trip. It is an attempt to build a fully functioning, permanently sealed civilization, one with zero chance of outside help if anything goes seriously wrong along the way. And even if every single piece of this puzzle somehow works perfectly, the ship still has to solve one final physics problem that nobody talks about nearly enough. After spending centuries building up incredible speed, how does a ship carrying an entire civilization actually slow back down once it finally reaches its destination? Speeding up and slowing down require the exact same amount of energy, a rule built directly into the basic physics of motion. This creates one of the most overlooked problems in every serious interstellar travel concept. A spacecraft does not just need enough fuel to reach incredible speed. It needs an equal amount of fuel, stored separately, just to stop once it finally arrives. Picture a car speeding down a highway with absolutely no brakes installed. Getting up to highway speed feels great, right up until the moment the driver realizes there is no way to slow down before reaching their destination. A generation ship or any high-speed interstellar probe faces this exact same brutal math. Every ounce of fuel used to accelerate toward a distant star has to be matched by an equal reserve, carried the entire distance, just to decelerate on arrival. This single requirement roughly doubles the total fuel and energy needed for any interstellar mission. Remember the antimatter cost explored earlier, or the almost impossible energy demands of a warp bubble. Every one of those staggering numbers assumed only the acceleration phase of the trip. Add a matching deceleration phase, and the total energy requirement climbs even higher, pushing already extreme concepts even further out of reach. Some proposed missions try to sidestep this problem entirely by never planning to stop at all. Breakthrough Starshot, the laser-powered probe concept explored earlier, aims to fly past Alpha Centauri at high speed rather than slowing down to enter orbit. This means the tiny probe would have only a brief window, likely just hours, to gather data and beam images back to Earth before shooting past the star system forever, continuing outward into deeper space with no way to turn back or slow down. For a generation ship carrying actual living people, flying past the destination is simply not an option. Passengers need the ship to actually stop, allowing time to study, land on, or settle near their target world. This means designers have proposed creative deceleration methods beyond simply carrying double the fuel. Some concepts suggest using a magnetic field to catch and push against charged particles in the interstellar medium, essentially using space itself as a kind of natural brake, similar to how a parachute uses air resistance to slow a falling object. Other researchers have proposed deploying a massive sail near the destination star, using the star's own light and stellar wind pressure to gradually slow the ship down over the final stretch of the journey. The same basic principle used to speed a solar sail up, just working in reverse. Every one of these ideas remains theoretical, tested only through computer simulations rather than real spacecraft. This deceleration problem sits quietly behind every impressive number explored so far. A ship capable of reaching 10% of light speed still needs a way to shed that same speed completely before arrival, without slamming into the destination system at a velocity that would instantly destroy the ship and everyone inside it. Even solving speed, fuel, food, and centuries of social stability still leaves one final, quiet danger waiting. What happens if something goes wrong along the way that has nothing to do with physics at all, something buried instead inside the fragile, unpredictable nature of the people making the journey? Every generation ship concept relies on one assumption that sounds simple, but might be the hardest part of the entire mission. It assumes that every single person born aboard the ship will keep believing in a destination they will never personally choose and might never even see. Consider what that actually means across 400 years. The original crew leaves Earth fully committed, having trained for years and volunteered for an enormous historic mission. Their children grow up hearing about Earth secondhand, through stories and old recordings rather than personal memory. By the 5th or 6th generation, nobody aboard has ever seen Earth, spoken to anyone who lived there, or experienced anything except the inside of the ship. The distant, half-remembered destination star might start to feel less like a promised future, and more like an old myth, repeated out of tradition rather than genuine belief. Historians studying isolated human communities on Earth have already seen versions of this pattern play out. Small, cut-off societies sometimes drift dramatically from their founding purpose within just a few generations, developing entirely new beliefs, priorities, or even open resistance to decisions made by ancestors nobody currently alive ever personally knew. Scale that same drift across 4 centuries, inside a sealed metal ship with no outside contact at all, and researchers studying generation ship psychology consider social collapse a serious, realistic risk rather than a distant worry. Mechanical failure adds another layer of danger. A spacecraft built to function perfectly for 400 consecutive years faces engineering challenges unlike anything humans have ever tested. The Voyager probes, humanity's longest-running spacecraft, have needed constant remote adjustments and shrinking power output just to survive 50 years, and they carry no human passengers at all. A generation ship would need life support systems, structural integrity, and power generation to hold up for 8 times that long sealed shut, with repairs handled entirely by descendants who never personally built the original equipment and may not fully understand every system inside it. Then there is the destination itself. Scientists studying Proxima b, the potentially habitable planet explored earlier, still do not know for certain whether it could actually support human life. It might have no protective magnetic field, leaving it exposed to dangerous radiation from its small active star. A generation ship could complete this staggering centuries-long journey only to discover the target world is completely uninhabitable, stranding everyone aboard with no realistic way to reach anywhere else. Every one of these risks connects back to a genuinely disturbing possibility. Humanity could build the ship, launch the mission, survive the physics, and solve the deceleration problem, only to lose the entire effort along the way to a broken engine, a collapsed society, or a destination that turns out to be far less welcoming than the data ever suggested. This uncertainty raises an important question about staying connected to a mission like this from Earth's side. If a ship spends centuries crossing the darkness between stars, how would anyone back home even know what happened to it? And how far could a simple message actually travel before fading into complete silence? A message sent from Earth travels through space at the speed of light, the fastest possible speed anything can move. That sounds impressive, until you calculate exactly how far a radio signal can realistically reach before background noise from the rest of the universe completely drowns it out. Voyager 1 still communicates with Earth today, but only because engineers built its antenna and radio equipment with extreme precision, and because massive dish antennas on Earth, some spanning over 200 feet across, work together to catch its signal. Even with all that effort, the signal Voyager sends home has grown incredibly weak, dropping in strength the farther the spacecraft travels. Scientists compare receiving Voyager's current signal to detecting a flashlight's glow from thousands of miles away, using instruments precise enough to catch the faintest possible flicker of light. This weakening effect follows a rule called the inverse square law. Every time the distance between a transmitter and receiver doubles, the signal strength drops to 1/4 of what it was. Double the distance again, and it drops to 1/16. This effect compounds rapidly, meaning a signal loses strength far faster than the distance itself increases. By the time a message crosses even a handful of light years, the original strong pulse has weakened into something almost indistinguishable from random cosmic static. The universe itself adds constant background noise into the mix. Stars, galaxies, and leftover radiation from the beginning of the universe all produce weak radio signals that fill space in every direction. A deliberate message from a distant spacecraft, or theoretically from another civilization somewhere out there, has to somehow stand out above all of that natural noise, using either an extremely powerful transmitter or an extremely sensitive receiver on the listening end. Scientists working on the search for extraterrestrial intelligence, an organised effort listening for possible alien radio signals, have calculated that even Earth's most powerful intentional broadcasts could likely only be detected by an alien civilization within a few hundred light years, assuming that civilization had technology at least as advanced as our own for catching faint signals. Beyond that range, any message humanity has ever sent essentially disappears into the overwhelming static of the wider galaxy. This creates a sobering reality for any generation ship attempting a centuries-long journey. Communication with Earth would grow weaker and weaker with every passing year, eventually becoming so faint that meaningful conversation becomes completely impossible, replaced by nothing more than occasional, barely detectable pulses confirming the ship still exists somewhere out in the dark. Descendants born decades into the mission might grow up in near-total silence from the world their great-grandparents once called home. If reaching a single nearby star already pushes communication past its breaking point, the scale of what lies even farther out becomes almost impossible to comprehend using anything explored so far. Our own galaxy, the Milky Way, stretches so wide that light itself needs tens of thousands of years just to cross from one edge to the other, a distance that makes even Proxima Centauri look like a single step onto a porch. Step outside on a clear night, far away from city lights, and you might catch a faint hazy band stretching across the sky. That soft glow is the edge-on view of our own galaxy, the Milky Way, seen from the inside looking out along its flat disc-shaped body. Our entire sun, along with every star visible to the naked eye, sits inside this single enormous structure, one of hundreds of billions of galaxies scattered across the wider universe. The Milky Way stretches roughly 100,000 light-years from edge to edge. To put that number beside something already explored, remember that reaching just our nearest star system, Alpha Centauri, required crossing about 4 light-years. The full width of our galaxy is roughly 25,000 times farther than that single, already extreme journey. Our Sun sits nowhere near the centre of this vast structure. It orbits about 26,000 light-years out from the galaxy's middle, tucked inside one of several spiral arms that wind outward like the arms of a massive pinwheel. From our position, Reaching the true outer edge of the Milky Way's disk would still mean crossing tens of thousands of light years in one direction, while reaching the crowded, energetic core would mean crossing a similar distance the other way. Here is a comparison that helps this click into place. If the entire Milky Way were shrunk down to the size of the continental United States, our solar system would take up a space smaller than a single grain of sand, sitting somewhere between the coasts. Every star you have ever seen with your own eyes fits inside a patch smaller than a few counties. The vast majority of our galaxy remains completely invisible to human eyes, hidden not by darkness, but simply by mind-bending distance. Scientists studying the Milky Way structure have identified a faint, extended halo of scattered stars and dark matter, stretching out even farther than the main visible disk, possibly doubling or tripling the galaxy's true total width once every hidden component gets included. Reaching the true, absolute edge of our galaxy, halo included, could mean a distance even more staggering than the already enormous 100,000 light-year figure most people picture first. Could humanity ever physically reach that true edge? Every propulsion idea explored so far, even the most optimistic theoretical warp bubble concepts, would take such an enormous amount of time and energy that the very idea stretches far past anything resembling a realistic mission. This is not a matter of centuries anymore. It is a scale that makes even a 400-year generation ship trip to Proxima Centauri look almost trivially short by comparison. Understanding the true size of our own galactic home changes the entire meaning of interstellar travel. Reaching a neighbouring star no longer looks like true galactic exploration. It looks like stepping just barely outside your own front door onto a porch attached to a house so massive that walking its full length would outlast every civilization humanity has ever built, combined. Human civilization, measured from the first known writing systems in ancient Mesopotamia, stretches back roughly 6,000 years. Every empire, every war, every invention, every single piece of recorded human history fits inside that relatively short window of time. Now compare that number to how long it would take light itself, the fastest thing in the entire universe, to simply cross from one edge of the Milky Way to the other. Crossing our galaxy at light speed would take about 100,000 years. Stretch that comparison out using something familiar. If all of recorded human history represents a single day, crossing the Milky Way at the fastest possible speed allowed by physics would take over 16 days straight, using that same shrunken timescale. Civilization has not existed long enough, even multiplied many times over, to match the raw scale of just crossing our own galactic neighbourhood. No spacecraft humans have ever built, or even seriously designed on paper, comes anywhere close to reaching light speed itself. Remember the earlier exploration of Einstein's absolute speed limit, the wall built directly into the structure of space and time that no object with mass can ever fully reach. Even a theoretical ship somehow reaching 99% of light speed, faster than anything currently considered possible, would still take slightly over 100,000 years to cross the galaxy from our current position near the edge. Here is where the deeper weight of this scale really sinks in. A generation ship attempting the 400-year trip to Proxima Centauri already stretches across roughly 20 human generations. Crossing the entire Milky Way, even at the fastest theoretical speeds explored anywhere in this series, would stretch across literally thousands of generations, a number so large that the ship's descendants would likely evolve, culturally and possibly even biologically, into something almost unrecognizable compared to the original crew who first left Earth. Scientists who study the deep future of human civilization sometimes describe this kind of scale using a term called deep time, a way of thinking about stretches of time so enormous that ordinary human comparisons stop being useful at all. Crossing the galaxy does not fit inside deep time the way a long historical era does. It stretches across a scale closer to how long entire species have existed on Earth, or how long it took a life itself to evolve from simple, single-celled organisms into complex creatures capable of building spacecraft in the first place. This reveals something important about how interstellar travel actually scales. Reaching a nearby star, however difficult, remains at least loosely connected to human timeframes, something a determined multi-generational effort could theoretically attempt. Crossing an entire galaxy exists in a completely different category, one where human civilization itself, in its current form, likely could not survive intact long enough to complete the journey, even using the most extreme theoretical propulsion physics allows. And the Milky Way, as impossibly vast as it already sounds, is still just one galaxy among hundreds of billions scattered across the wider universe. Beyond its edge lies something even stranger than empty interstellar space, a region so profoundly empty that scientists needed an entirely new word just to describe how little exists there. Inside a galaxy, space feels crowded compared to what waits beyond it. Stars, planets, gas clouds, and scattered dust fill the Milky Way in numbers, reaching into the hundreds of billions. Step outside the galaxy's edge, into the vast gap separating it from its neighbours, and the universe becomes almost unimaginably emptier, a region scientists call intergalactic space. Remember the interstellar medium explored earlier, the thin scattering of atoms found between individual stars within our own galaxy, averaging roughly 1 atom per cubic centimetre. Intergalactic space makes that already thin material look crowded by comparison. Out in the vast gaps between galaxies, the average density drops to somewhere around 1 atom per several cubic metres, a difference so extreme that some regions qualify as the emptiest spaces scientists have ever measured anywhere in the observable universe. Astronomers have mapped this emptiness using something called the cosmic web, a large-scale structure connecting galaxies together through faint filaments of gas and dark matter, similar to how a spider's web connects distant points using thin, nearly invisible threads. Between these filaments sit enormous regions called cosmic voids, areas of space so empty that some stretch across hundreds of millions of light-years without containing a single significant galaxy inside them. One of the largest known voids, called the Bootes void, spans roughly 330 million light-years across, an emptiness so vast that if our own Milky Way sat directly at its centre, astronomers here would not have discovered the existence of other galaxies until the 1960s, simply because nothing bright enough would have existed close enough to notice sooner. Living inside a void like that would mean growing up believing your own galaxy was essentially alone in the universe. Here is what makes intergalactic space especially strange compared to everything explored so far. Unlike interstellar space within our galaxy, which still contains scattered stars and occasional planetary systems worth studying, most of intergalactic space contains nothing meaningful for a spacecraft to interact with at all. No stars to study up close, no planets waiting to be explored, simply an overwhelming stretch of near total emptiness separating one island of stars from the next. This raises an uncomfortable question about any mission attempting to leave the Milky Way entirely. Every challenge explored throughout this series — fuel, time and deceleration, generational survival, radiation exposure — becomes dramatically worse once a spacecraft leaves the relative safety of a galaxy behind. There would be no nearby star to adjust course toward if something went wrong. No possible rescue, no nearby resource to gather, nothing except open darkness stretching in every direction for millions of light-years at a time. And yet, despite all of that crushing emptiness, our own galaxy is not entirely alone out there. Just past this vast gap sits our closest large neighbouring galaxy, one visible even to the naked eye on a clear night. A galaxy so close on a cosmic scale that scientists consider it almost a companion to our own, even though reaching it would still require crossing a distance that makes everything explored about our own galaxy look small by comparison. On a clear, dark night, far from city lights, a patient observer can actually spot the Andromeda galaxy with nothing more than their own eyes, appearing as a faint, blurry smudge of light. This makes Andromeda the single most distant object visible to the naked human eye, and also our closest large galactic neighbour, sitting roughly 2.5 million light-years away from the Milky Way. Here is what makes that number strange to sit with. Every star you have ever personally seen in the night sky belongs to our own galaxy, sitting at most a few thousand light-years away. Andromeda sits so much farther out that the light reaching your eyes tonight actually left that galaxy 2.5 million years ago, long before modern humans even existed on Earth. You're not just looking at a distant place, you're looking directly into the deep past. Despite that staggering distance, astronomers consider Andromeda genuinely close by cosmic standards, almost a next-door neighbour compared to the countless other galaxies scattered across the wider universe. Both galaxies belong to a small cluster of gravitationally connected galaxies called the Local Group, and they are not simply sitting still relative to each other. Andromeda is actually moving toward the Milky Way, pulled by gravity, closing the gap between the two galaxies at roughly 250,000 miles per hour. Scientists studying this motion predict that the Milky Way and Andromeda will eventually collide and merge together into a single, larger galaxy, an event expected to begin in about 4 billion years. This is not a violent star-smashing collision the way it sounds. Individual stars sit so far apart, even within a crowded galaxy, that the two galaxies will likely pass through each other with almost no direct stellar collisions at all, slowly reshaping into a completely new galactic structure over hundreds of millions of years. None of this makes Andromeda reachable using anything close to current or even near-future technology. Even at Andromeda's approaching speed, it would still take billions of years to close the remaining gap naturally. A theoretical spacecraft attempting the trip directly, even using the fastest speeds explored anywhere in this series, would still need millions of years just to cross the distance separating the two galaxies. This creates one of the strangest contradictions in all of astronomy. Andromeda genuinely counts as close, practically a next-door neighbour, when measured against the true scale of the universe. It remains completely, permanently out of reach for any realistic human mission, even one stretched across countless future generations. Distance and reachability, it turns out, do not always mean the same thing once numbers grow large enough. If our closest large galactic neighbour already sits this far beyond anything humanity could ever physically visit, the true scale of everything else still waiting out there becomes almost impossible to hold in your mind. Beyond Andromeda, beyond every galaxy visible through even the most powerful telescopes ever built, lies a boundary unlike anything explored so far, one that does not mark the edge of space itself, but instead marks the very limit of what light has ever had enough time to show us. Telescopes let scientists see incredibly far into space, but there is a hard limit to how far any telescope, no matter how powerful, could ever possibly look. That limit is called the observable universe, and understanding exactly why it exists reveals something strange about the true structure of reality itself. The universe began roughly 13.8 billion years ago, in an event scientists call the Big Bang. Since light needs time to travel across any distance, and since the universe itself has only existed for that specific stretch of time, there is a hard boundary on how far light from any distant object could have possibly travelled to reach us by now. Anything sitting far enough away that its light has not had enough time to arrive yet remains for now completely invisible, no matter how advanced our instruments become. Here is where the numbers get genuinely strange. Simple math might suggest the observable universe should measure exactly 13.8 billion light-years across in every direction, matching the age of the universe itself. The actual measured size is far larger, stretching about 93 billion light-years across from edge to edge. This happens because space itself has been continuously expanding this entire time, stretching the distance between us and those ancient light sources even while their light was still travelling toward us. Think of it like a rubber band with two dots marked on it. Even if something moved from one dot to the other at a fixed, steady speed, stretching the rubber band the whole time would mean the total distance travelled ends up being longer than the dot's original separation, once you account for how much the band itself grew during the trip. Light behaves the same way, crossing an amount of expanding space that adds up to something far larger than its simple travel time might first suggest. This creates an important distinction most people never learn. The edge of the observable universe is not a real physical wall sitting out there in space, waiting to be reached or touched. It simply marks the current limit of what light has had enough time to show us, a boundary that actually grows wider every single year as light from slightly farther objects finally finishes its impossibly long journey to Earth. Beyond this visible boundary, the universe almost certainly keeps going, likely containing far more galaxies, far more stars, and possibly a mind-boggling amount of space that human eyes and instruments may never see. Not because nothing exists out there, but because light from that region has simply not had enough time to reach us yet, and may never get the chance to. This raises an unsettling question buried inside the very structure of the cosmos. If the observable universe keeps expanding every single year, as more ancient light finally arrives, does that mean humanity could theoretically see farther and farther over time? Or is something else happening out there, some deeper property of space itself, working actively against us, making certain regions permanently unreachable no matter how much time passes. Space itself is expanding, not just the empty gaps between planets or stars within a single galaxy, but the actual fabric connecting every distant galaxy to every other galaxy across the entire universe. Scientists first confirmed this using observations made by astronomer Edwin Hubble in the 1920s, who noticed that nearly every distant galaxy appeared to be moving away from us, and the farther away a galaxy sat, the faster it appeared to be retreating. This discovery, now called Hubble's law, revealed something deeply strange about the structure of reality. Galaxies are not simply flying apart through space, the way debris scatters after an explosion. Instead, the space between them is stretching, carrying galaxies farther apart the same way dots painted on a balloon spread apart as someone blows air into it. The dots themselves barely move relative to the balloon's surface. The surface stretching underneath them does all the actual separating. Here is where this connects directly back to Einstein's unbreakable speed limit explored earlier. Nothing with mass can move through space faster than light. That rule remains completely true and unbroken. But space itself is not an object with mass, meaning the rule limiting normal motion simply does not apply to how far space can stretch. Given enough distance, the combined stretching of space between 2 points can add up to a separation speed faster than light itself, without either galaxy actually breaking any law of physics. Scientists studying this effect have identified a specific calculable distance where this crossover happens, a point roughly 14 billion light-years away called the Hubble radius. Beyond that distance, galaxies are currently retreating from us faster than light could ever cross the growing gap between us, even though those galaxies themselves are not technically moving through their own local space any faster than normal. This creates a genuinely bizarre situation. Light from galaxies beyond this specific point could theoretically be travelling directly toward Earth at its full normal speed and still never actually arrive, because the space it needs to cross keeps stretching wider, even faster than the light itself can close the gap. Imagine running toward a finish line as fast as physically possible, only to have the entire track keep stretching out ahead of you faster than your own legs can carry you forward. Modern measurements have revealed something even stranger layered on top of this. The rate of this cosmic expansion is not staying constant. It is speeding up, driven by a mysterious force scientists call dark energy, something detected clearly through its effects, but still not fully understood even by leading physicists today. As time passes, more and more distant galaxies will cross that critical threshold, their light permanently unable to ever reach us, no matter how much time the universe has left. This reveals something profound and unsettling about the true limits facing humanity. Distance alone was already an enormous obstacle throughout everything explored in this series. Now something else stands in the way, an active, accelerating force built into the structure of space itself, one that does not just make certain places far away, but actively pushes some of them permanently, mathematically beyond any possible reach, no matter how advanced human technology might someday become. Every year, more of the universe slips permanently out of reach. This is not a slow, gentle process happening somewhere in the distant future. It is happening right now, driven by the same accelerating expansion explored in the last chapter, and it defines something scientists call the cosmic horizon, a genuine, mathematically real boundary marking the absolute limit of what humanity, or anyone else in the universe, could ever possibly reach. Picture standing on a beach as the tide slowly rises. At first, the water only reaches your ankles, and dry sand still stretches out ahead of you in every direction. As the tide keeps rising, the dry area shrinks, not because the beach itself moved, but because the water kept climbing higher, claiming more ground with every passing minute. The cosmic horizon works in a strangely similar way, except instead of water rising, it is space itself accelerating outward, permanently claiming distant galaxies and placing them forever beyond any possible contact. Here is the difference between this and the observable universe explored earlier. The observable universe describes what we can currently see, a boundary that keeps growing slightly every year as ancient light finally finishes its long journey toward Earth. The cosmic horizon describes something else entirely, the absolute limit of what we could ever theoretically travel to or communicate with, even using a beam of light, and given infinite time to make the journey. Because of accelerating expansion, that second boundary is actually shrinking, not growing, trapping fewer and fewer galaxies within permanent reach as time goes on. Scientists have calculated that galaxies beyond a certain distance, roughly 16 billion light-years away today, have already crossed this critical threshold. Their light, and any theoretical spacecraft launched from Earth today, could travel at full light speed forever and would still never reach them, because the space separating us keeps stretching faster than anything could ever close that gap. This means some galaxies visible through today's most powerful telescopes are technically already unreachable, frozen forever just beyond an invisible wall that no engine, no matter how advanced, could ever cross. Their light still reaches us for now, a ghostly signal sent long before this boundary sealed shut, but any physical journey toward them has already become permanently, mathematically impossible. The genuinely unsettling part is that this horizon keeps tightening. Every year, dark energy pushes slightly more distant galaxies past the point of no return, shrinking the total portion of the universe humanity could theoretically ever visit, even under the most optimistic science fiction level propulsion imaginable. This is not a limit created by weak engines or unfinished technology, the same way earlier limits explored throughout this series eventually might get solved through future breakthroughs. This is a limit built directly into the expanding structure of the universe itself, one that grows stronger and more restrictive with every single year that passes. If distant galaxies keep vanishing behind this shrinking wall, an uncomfortable question follows directly behind it. Are we watching this process happen in real time, right now, with galaxies we can currently see slowly fading toward that same fate, destined to disappear from human view entirely before life on Earth ever gets the chance to reach them? Right now, tonight, somewhere in the night sky, distant galaxies are slowly beginning a process that will eventually erase them from view completely. This is not happening through galaxies physically disappearing or being destroyed. It is happening because the accelerating expansion of space is stretching their light so severely that it grows fainter, redder, and eventually undetectable, no matter how powerful future telescopes become. This effect connects directly to something called redshift. As space stretches between a distant galaxy and Earth, the light travelling toward us stretches along with it, shifting toward longer, redder wavelengths, the same way a sound wave stretches and drops in pitch as an ambulance speeds away from you. The farther away a galaxy sits, and the faster the space around it stretches, the more extreme this shift becomes. Eventually, light stretches so far that it moves completely outside the range human instruments, or any theoretically possible instrument, could ever detect. Astronomers have already identified specific distant galaxies currently approaching this fading threshold. Light from these galaxies still reaches Earth today, but each passing year, that light arrives slightly weaker and shifted slightly further toward wavelengths growing harder to detect. Scientists studying this effect predict that within roughly 100 billion years, nearly every galaxy currently visible beyond our own local group will have redshifted completely out of any possible detection, leaving future observers with a sky containing only our own merged galaxy and its closest immediate neighbours. Here is a strange thought worth sitting with. Some ancient civilization, if one existed billions of years in the future, born long after this fading finishes, might look up at their night sky and see almost nothing beyond their own galactic neighbourhood, having no way to ever know that trillions of other galaxies once existed and were fully visible to earlier generations. They would have no observable evidence the wider universe was ever there at all, purely because they arrived too late in cosmic history to see it, before expansion erased the view. Humanity happens to exist during an unusually fortunate window of cosmic time, one where the universe remains young enough that distant galaxies are still visible, still studyable, still within reach of powerful telescopes capturing their ancient light before it fades forever. Future generations, arriving far enough down this same timeline, would inherit a night sky permanently emptier than the one we currently study, regardless of how advanced their own technology might become by then. This does not mean galaxies currently visible will suddenly vanish within a single human lifetime. The fading happens across scales of time so enormous that any individual human generation would barely notice the difference. It does mean the window for observing, studying, and potentially someday reaching the wider universe beyond our own galactic neighbourhood is not permanent. It is slowly, quietly closing, one galaxy at a time, whether humanity ever attempts interstellar travel or not. If the universe itself is actively working to seal away everything beyond our own cosmic neighbourhood, an even bigger question emerges from everything explored throughout this entire journey. Is there an absolute final limit to how much of the universe humanity could ever reach, even given every possible future breakthrough and unlimited amounts of time to attempt it? Every barrier explored throughout this entire journey eventually funnels down into a single final number. Scientists studying the true physical limits of interstellar and intergalactic travel have calculated the absolute maximum size of the universe humanity, or any civilization anywhere, could ever theoretically reach, even using a spacecraft capable of travelling at the full speed of light, launched today and given unlimited time to keep travelling forever. This maximum reachable zone comes from combining everything already explored. Light speed remains the fastest anything could ever travel, a rule confirmed repeatedly and never broken. Meanwhile, the accelerating expansion of space, driven by dark energy, continuously pushes distant galaxies away faster and faster, eventually pushing them beyond a point where light could ever catch up, no matter how much time gets thrown at the problem. Balancing these two forces against each other, the fastest possible speed against the ever-accelerating stretch of space itself, produces one final, absolute limit. Scientists estimate that a beam of light launched from Earth today could theoretically still reach galaxies currently sitting up to about 16 billion light-years away, but nothing beyond that distance, ever, no matter how much time passes afterward. Everything past that specific boundary has already crossed, or will eventually cross, into permanently unreachable territory, sealed away by expansion faster than pure light speed could ever overcome. Here is what makes this number so strange compared to every other limit explored throughout this series. Every earlier barrier, chemical rocket fuel limits, antimatter production costs, warp bubble energy requirements, radiation danger, even generational social collapse, represents a problem humanity could theoretically solve someday, given enough time, enough resources, and enough scientific breakthroughs. This final limit is different. It is not an engineering problem waiting for a clever solution. It is a permanent, built-in feature of how the universe itself is expanding, one that no future technology, no matter how advanced, could ever engineer its way around. This means humanity's ultimate cosmic reach, the absolute maximum boundary of what could ever be physically visited or contacted across all of time, sits already fixed and shrinking, regardless of anything humans do or build going forward. Civilizations born earlier in the universe's history, existing back when this reachable zone was larger, would have had access to a bigger slice of the cosmos than we do today. Civilizations arriving even later than us will inherit an even smaller reachable region than the one available right now. Scientists describe this using a term called the future visibility limit, a permanent ceiling placed not by human ambition, engineering skill, or available resources, but by the actual physics governing how space itself behaves at the largest possible scale. It represents the single largest, most absolute wall standing between humanity and the wider universe, one that exists whether or not anyone ever attempts to reach it. This brings everything explored throughout this entire journey back to the original question asked at the very beginning. If humanity had truly infinite time, unlimited resources, and every possible future scientific breakthrough imaginable, would there still be a final, unbreakable wall standing between us and the rest of the universe, one that no amount of ambition or ingenuity could ever fully overcome? Give humanity infinite time, remove every current limit on money, engineering, and available energy. Imagine breakthroughs beyond anything explored throughout this entire journey. Solved fusion power, mastered antimatter production, a fully functional warp bubble, even some currently unknown physics nobody has discovered yet. Even with every single one of those problems solved completely, one final wall would still remain standing, untouched by any of it. That wall is the accelerating expansion of space itself. Every barrier explored earlier in this journey — distance, fuel, radiation, generational survival, deceleration, communication delay — represents a challenge built from engineering and biology. The kind of problem human ingenuity has repeatedly found ways to work around throughout history. The expansion of the universe is not that kind of problem. It is not waiting for a clever solution. It is a fundamental property of the cosmos itself, written into the same physics that gives us gravity, light, and time. Here is the full weight of what that actually means. A civilization could theoretically survive for trillions of years, mastering every scrap of physics currently known and countless discoveries still waiting to be found, and it would still watch galaxies slip permanently beyond reach, one by one, exactly as explored in the last few chapters. No amount of patience changes this. No amount of speed changes this either, since nothing can ever exceed the speed of light, while space itself faces no such restriction at all. This means the reachable universe is not simply large. It is finite, fixed, and shrinking. A specific, calculable region surrounding our position, permanently separated from an ocean of galaxies drifting forever beyond any possible contact. Everything ever explored about the impossible distances to nearby stars, the staggering scale of our own galaxy, the almost incomprehensible gap separating us from Andromeda, all of it sits comfortably inside this reachable zone. It is everything past that zone, the true majority of the wider universe, that remains locked away permanently, regardless of how far human ambition eventually reaches. Voyager 1 is still out there right now, carrying its golden record through the dark, moving at a speed that once felt impossibly fast and now looks almost laughably small compared to everything explored across this entire journey. It represents humanity's single farthest step outward, a machine that took decades just to leave our own solar system's front porch. The wall standing beyond it, beyond every star, beyond our entire galaxy, beyond even our nearest galactic neighbour, was always going to be there, quietly expanding, long before humans ever built a single rocket. This is the true answer to the question asked at the very beginning. How far could humanity really travel before the universe stops us? Not a distance measured in miles, or light years, or even galaxies. A boundary measured by the very fabric of space itself, growing wider every single day, sealing away pieces of the cosmos faster than light itself could ever hope to follow. Somewhere out past every star we will ever see, galaxies are already drifting beyond our reach forever, vanishing into a darkness no ship, no signal, and no amount of human determination could ever cross. That is the wall. We found it.